fifth drill video for this semester. Today we're going to start talking about linear models. We're going to make null models and one parameter models. If you haven't already installed the PSYC package, go ahead and install that package here. And we'll begin with loading in our libraries, the tidyverse and PSYC. And we're going to read in some data that we'll refer to as the bias data, and I'm pretty sure you'll probably see this data again throughout the semester. We're only using part of it for today, and but there's a lot that can be built on with this particular data set. So note that because this is a .dat file, that we need to use read_tsv, not read_csv. And so once you read in data, you should always explore your data a little bit, take a look at it. So we'll take a glimpse just to see what all variables exist in here, and we want to figure out what are these data, and what was this study looking for, what was its design, etc. So we'll briefly discuss that before we start getting into very much. So we see that sub ID is a character variable. Obviously, that's going to be our subject ID. So even though it looks numeric, it's in R as a character, which is fine because really it's a factor anyway. It's not supposed to be a numerical value. Then we have something called condition, things called concern 1 through concern 4, and then base IAT, week 4 IAT, and week 8 IAT. So this study, for those of you who may not be familiar with IATs, the way that they work is you're shown some stimuli, and the task is to, as quickly as possible, categorize some image or word, some sort of stimuli, as either one category or the other. So in this case, this is a race IAT. So for instance, the participants might be instructed to put their fingers on the Q and P buttons, or maybe it's the left and right arrow, maybe they have an actual dedicated button box that only has a left and right button. Whatever the case may be, I'll just refer to it as respond to with the left button or the right button. So they have to respond to these things as quickly as possible. And so it'll cycle through pictures. And so, for instance, it might start by saying to categorize pictures as either European Americans or African Americans. So a picture pops up, and if it's a European American, then you quickly hit the left button. If otherwise, you quickly hit the right button if it's African American. And then, so you'll do a bunch of trials, go through a bunch of these different pictures, and then the labels will switch. So on the next time, it might be African Americans on the left and European Americans on the right. Well, then there's also a second group of categories. In this case, it's good versus bad. And so you might see some words, and you have to decide if the word that's shown is good or bad. And as soon as the word pops up, you have to, as quickly as possible, hit that left button if it's good, the right button if it's bad. And again, on other trials, it will flip those around and have bad over on the left and good over on the right. Now, where the IAT really comes from is once you combine those two things. So now you're shown mixtures of both words and pictures, and you hit the left button if it's European American or bad, and you'll hit the right button if it's African American or good. And then, like I mentioned earlier, that on other trials that'll flip around. So for say 40 trials, it'll be this way, and then the instructions will flip around. And for 40 trials, you'll be told if it's European American or good, click the left button. If it's African American or bad, click the right button. The logic with this is that what they're looking for is implicit biases. So rather than explicitly being biased against, in this case, minority individuals, it's looking for the implicit associations that you have about, in this case, minorities. So the logic is that if you say you have a bias against minorities, you will be able to respond faster when the label African American is congruent with your, implicit attitudes that if they are bad. So over in this case, whenever you see, a picture of an African American and you have to click African American or good, that disconnect between your idea of them actually being bad but the word saying good slows down your response a little bit. You're a little bit quicker to respond to African American or bad because they have a semantic link implicitly in your in your mind, essentially. So you can think about this as, and then they'll do the same thing for these word labels. So as it goes through all of these trials, essentially what you're doing is you're seeing if you put together the labels of, you know, African American and bad, are people quicker to respond to that? And if so, then they are said to have an implicit bias against, you know, African Americans. So in short, what we're looking at is this. We're looking at some IAT scores. So we have a baseline IAT score, and then 4 weeks later, after something, they do another IAT, and then on week 8 they have a third IAT. And so we're looking at their scores over time based on some other stuff. And we'll get into all that other stuff later, but for now all you need to know is that what these IAT scores are is some computation that essentially is a measure of implicit bias. So if we take a look at our descriptives for this bias data set, and as a reminder, you don't need this PSYC : if you ran library psych up here. You can just run describe bias and it'll run just fine. I put that there just to give you the reminder of where this function comes from. Similarly, if you just leave off, you can take off the library psych, and you don't have to load the whole psych library if you just run PSYC : describe, say if you're only running this one time. Anyway, you've seen this function before. Bill's had it up in some slides where it just gives you a range of descriptive statistics. And it's always good to look at these descriptive statistics whenever you're reading a data set, because it can give you a lot of information. You know, for instance, looking at your mins and maxes. When we look at condition, we see that we have a min and a max of 1, which tells us that there's only one condition in this data set. In other words, like this is a partial data set. It doesn't have multiple experimental conditions in this particular set. You know, for our concern scores, we have mins of 1, maxes of 9 to 10. So it looks like that's, you know, some sort of 10-point scale. But if one of these had, you know, a value of, you know, 100 or, you know, up in the 90s, and everything else is, you know, 1 through 10, that can stick out, and you can say, wait a second, this concern 3 that has, you know, this really high max, like we need to take a look at that. So that's the kind of stuff that you're looking through. You should check, make sure your ends, are we missing, are we missing things? You can take a glance at your means and medians and things, that may not necessarily matter. Your skew and kurtosis, again, a lot of those things are typically a lot more sensible whenever you look at them as graphs instead of just trying to interpret some skew number. But anyway, the real takeaway here is, you know, look at what these values are so that you can try to figure out, okay, what data do I have? So in this experiment, in this bias data, we're curious about people's change in IAT scores from baseline to week 8. So in other words, we want to see, has people, when they come in and do a baseline IAT and we measure their implicit bias, and then they come back 8 weeks later, is their implicit bias the same or has it changed? So we're going to create a variable called IAT change, which is that change over time. So all we're going to do, we take our bias data set and we pipe it into mutate, and we do our week 8 IAT minus the baseline IAT and create that IAT change variable. And so once we run that, make sure it's good, then we'll go ahead and store that back over the bias data set. That way now that's actually stored in our data. And now we can learn a little bit about this variable. So if we look at what our like the mean bias changes, it went, or the mean IAT scores went down by 0.241 with the standard deviation of 3.03. The minimum amount of change, well, I just realized that says that the minimum amount of change was negative 1.10, but I guess that should have been absolute values. We can change that. So the minimum amount of change is 0.00197. The maximum amount of change is 1.1. It happened to be in the negative direction, which we know from looking here, but that's beside the point. Just looking at this, like clearly there was some change from week 1 to week 8, so we can throw this into a ggplot just by piping our bias data set into ggplot and telling it x equals IAT change, and then adding plus sign to add a layer geom histogram, and just telling it the bin width. I just picked 0.2, which seemed like a decent thing. So here's what our histogram looks like of this change. So clearly, there was some changes in people's IAT scores, or else everything would just be 0. So now, if we start with a null model, or what might be called a stupid model, or a model with no parameters. So our p equals 0. That's not the probability p. This is the number of parameters p, and we're just saying that we want 0 to be our prediction. So first, we're gonna do this by hand. By finger quote hand. And so we're going to make some predictions about the IAT scores, or the change in the IAT scores. And since we have no information, because we're just going to predict 0 for everyone. So literally, this line here, all we're doing is we are creating a variable called predict0 and giving it the value of 0 for everyone. So if we predict 0 for everything, now let's compute the total prediction error. So if for this person here, if we predict 0, but the actual change is it went down by 0.374, then if we subtract 0 from negative 3.74, it will give us how far off from the prediction was the actual value. So here, all this is doing is it's saying take the bias data and create a variable, mutate to create a variable called square.errors.0, and that variable will be the IAT change, this column, minus predict0, this column, and we're going to square that. So we will take, for each participant, we take this value, subtract 0, and square it. This value, subtract 0, and square it. Once we do that, we now have this column that is the squared errors. And in terms of why we square those errors, you have to think in terms of, similar to this problem up here where I had initially forgot to put in the absolute value. And when I just say what's the minimum change, because there are negatives, that changes things. And in terms of error, if you don't square it, you'll have negatives in your data, and it all balances out to 0. But when you square it, you get rid of all those negatives, because the error can't be negative. It is just how far off is it. It's an absolute. It's not a negative thing. So if we want to look at what we've done so far visually, I'm going to open up a new window here. None of this is in the script, so if you're wondering where all this is coming from, it's like, don't think that you're missing something in the script that's in front of you. But if I make this plot that I have the IAT change variable, and here on the x-axis we just have subject ID, so it's just in the order of the experiment, like the participant number order, and just because that is visually a little bit weird, all I'm going to do is sort the x-axis as a function of increasing y. So, you know, this participant here is actually put first, and then this participant is second, and then this participant's third, and then these three people here are over here. So point is that when we see this, this is just plotting our data. I just sorted it to make it easier to see. So, so here's what our data look like. And in this case, again, we predict 0 for everything. So if our predictions are these gray dots, so for this participant, we predict 0. And then for this participant, we predict 0. And for this participant, we predict 0. If you draw a red line between each of those things, this red line is the error visualized. So you can see on some of these predictions, like there's very, very little error. On some of these predictions, there is a lot of error. So now that we have, that's what these red lines represent, this IAT change minus predict.0. And then once you square those values, they all become positive, and then we can sum up those errors to get the sum of squared errors. So that's what we're going to do here. And we can see that our sum of squared errors is 11.63482. Now, you may be wondering why I summed it up this way by selecting that one particular column and then running it through sum instead of using summarize. And the reason will become a little more obvious here in a little bit, but the long story short is that I wanted to create a single numeric value for an object called SSE0, so that instead of returning a tibble, a 1-by-1 tibble, I wanted just one specific value in this case, which is why I used sum instead of just bias and then summarize sum of square error 0. So again, let me just make that a little more clear here. I could have said bias summarize sum square error 0, and it will return that 11.63487. But now if I store this as a sum object, then instead of the object being a single value, then that object would be a tibble. So I'd still have to call the value from this tibble. So that's the reason that I did not do it this way, just to be clear. So what we know now is that our sum of squared errors is 11.63, but we have no way of knowing whether or not that model is any good. So we will then instead consider a one parameter model, or an intercept only model, or a mean only model. And in this case, we're going to buy one piece of information. Bill talked about the idea of degrees of freedom being kind of this, how many, that statistical currency, and buying things with those degrees of freedom by buying parameters. And so in this case, we want one parameter in our model, and that one parameter is the mean. That one piece of information that we have is the mean of IAT change. And so in this case, all we're going to do is, just like the last time, we're going to make a prediction, but this time instead of predict 0, I made this predict m for predict mean. And instead of predicting 0 for each and every IAT change score, we'll predict the mean for each and every IAT score. So the mean IAT change is negative 2.41. So instead of predicting 0 for everything, we're going to predict that mean instead. Just like before, we can find the difference between the actual change, the actual value, and the predicted value, and square it to get our squared errors. And then we can sum those to get our sum of squared errors. Now again here, basically what we're doing is, instead of predicting 0 for each of our values, and if you recall, we had this here, and all this red lines being the error. So now if we instead predict the mean, which is here at, what did we say it was? Negative 0.241. So these orange dots are our predictions instead of these real light gray dots where they used to be. So then, just like before, we find the difference between the predicted values and the actual values. And when we do that, we now have these green lines that represent our error of this model. And so if you square these green lines, the distance, the length of these green lines, and then sum them all up, it will sum to 7.089585. But again, just because the sum of squared errors is smaller, that doesn't necessarily mean that the model is better. And we have to compare the models, because as we've talked about, or as Bill's talked about, including additional parameters is almost necessarily going to improve your model sum and reduce that error sum. At a minimum, it won't make sum of squared errors bigger to increase or to add additional parameters. So it's almost guaranteed to decrease your sum of squared errors when you include additional parameters. But the question is the juice worth the squeeze? So does it make sense? Is it worth it to include that additional parameter? Because if you include an additional parameter and your sum of squared errors barely goes down, then it's not worth it to include that, because that doesn't significantly reduce your error. So that's what it comes down to, is a question of, does this significantly reduce your error? And so the way that you figure this out is by looking at the F statistic. And so here we're going to run in row, which is just the number of rows. And I'm going to store that as a variable called n, and all that's going to do is store the number of observations in the data frame as a thing. Now earlier, like I said, that I wanted to specifically have the sum of squared errors for, well, I labeled that 1. I guess I should have called that m. Sorry, I didn't change that from previous things. It'll be m by the time you see it, and I apologize for that. But the reason that I stored those as objects was so that we could put them within this formula, because the formula for your F statistic is going to be the difference between your sum of squared errors for the null model and the intercept only model, that means only model, or to use the language that you'll consistently hear, the compact model, which means that smaller model that has fewer parameters than the augmented model, which is the full model. So your compact model isn't always going to be the null model. In this case, it is. So our compact or null model, or when we have our sum of squared errors for that, which again is 11.63, and then here is our sum of squared errors for the means only model. So we get the difference between those two things and divide it by the number of the difference in the number of parameters in the augmented model versus the null model or compact model. And then all of that will be over the sum of squared errors for the means only model over the degrees of freedom. So how many bits of information could there have been additionally? So our n here we already saw is going to be that 78, and then so our n minus 1. When we run this formula and we have our f stat, we see that f equals 49.36581. Now we can get a p-value with this f statistic to see, is this f value significant. So to do this, we need 3 pieces of information. We need the f value, we need the degrees of freedom for the numerator, and the degrees of freedom for the denominator. The degrees of freedom for the numerator is how many more models are in the or how many more parameters are in the augmented model over the compact model. We have 1 parameter in our augmented model and 0 parameters in our compact model. So 1 minus 0, our df numerator is 1. And then our denominator degrees of freedom, again, is how many additional parameters could we have theoretically included, which is n minus 1. So our number of observations minus 1 is our df denominator, or 77. And then we use this function called pf, and in that we're going to put our f statistic, df numerator, df denominator, and then we'll tell it lower tail equals false, which means that we want it to give us the p-value for the probability of getting an f value larger than the f statistic if in fact the population mean is 0, as opposed to, you know, the 2-tailed test. Like in this case, we're wanting to do a 1-tailed test specifically. And before I run this line, I want to show you one quick thing. You'll notice that this line is wrapped in parentheses on both sides. So here, for instance, you see where we ran this line, and all it does, it doesn't output what that f stat is. All it does is store it. And so then I have to have f stat here to actually print what was computed there. And all that wrapping things in parentheses like this does is it will compute this p-value, store it as a object called pval.xx, and then go ahead and print that value. So now we have a thing called pval.xx, but you can see here when we ran that, it also printed out that value. So occasionally you'll see me wrap things in parentheses just like this, because I do want to see I want to both store the value but also conveniently see the value that's being stored. So again, here, when we ran this one, it didn't run, but if I come back and I wrap that whole line in parentheses, now when I run it, it both stores that as fstat and shows me what the actual value is that it computed. And then the other thing that I want to point out is, Bill has mentioned this before, but whenever you get this scientific notation, you know, 7 point whatever, E, however many, digits, to turn off scientific notation, somewhere in your script, just run the function options, and you'll tell it scipin equals some number. I usually start with scipin equals 10, and basically this scipin argument tells R how many decimal places things need to go before converting to scientific notation. So in other words, now that we run scipin equals 10, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places over. That might not work sometimes, and you might have to, run it as scipin equals 15 or whatever the case may be to get it to work. But either way, you only have to run this once within a script, and then any scientific notation that is within that whatever boundary you put in is going to work. So you don't have to run like this options scipin equals 10 each time you're trying to run something. Now that is just, it will always give me that many decimal places out. So anyway, point is, we have our p-value is 0.000, and in this case, p is less than 0.001. do not, you don't need to, well, first of all, when you're reporting your p-values, you'll always hear me say, report your exact p-values, report your exact p-values, report your exact p-values. Like, don't get into the habit of p is less than 0.05. Report your exact p-values. The exception being, if p is less than 0.001, then just say p is less than 0.001. If p is, equals 0.01, then say p equals 0.01. Don't say, p is less than 0.05. But once p is less than 0.001, then that's as low as you really need to get with your p-values. But outside of that, report your exact p-values. And whatever you do, don't say, p equals 0. But moving on, now we'll look at how to simplify what we've just done by using LM. So it's important to do this kind of manual method to understand where all these values are coming from. But there's an easier way to do it, and that's with the LM function. And we're going to be using this a lot this semester. So this is the general linear model is LM parentheses. At the most basic level, there's two pieces of information that you put in it, which is the formula and the data. The formulas are written as y tilde x, which tells our, this could be read as y regressed on x, or y is predicted by x, or however you want to say it, whatever language is used in your field, or that was used in your previous classes, whatever makes sense to you, to say something, some outcome, and then here are some predictors. So whether you read this as y regressed on x or y predicted by x or whatever the case may be, it doesn't matter. So in our mean only model here, our intercept only model, we don't have any other predictors here. All we have is that the mean of the outcome. And so we're going to tell R that we want to include that the mean of the outcome as the parameter in this model. So the way that you do that in LM is by telling R, you use the 1 as the outcome. So I want to be absolutely clear on this, that this is not telling R that it is IAT change predicted by 1. Don't think of this as the number 1. Whenever you see this 1 digit inside LM, in your head say the intercept. That is the intercept. It means the intercept, or the mean of the outcome. So again, don't think that this is the intercept. Now, one thing is that I'll show you that we have this data equals, and then I have a period here. If you go back to the tidyverse video where we briefly talk about pipes, and I mentioned that sometimes some functions aren't built the way tidyverse is, that where all tidyverse functions expect the data as that first argument. And so when the pipes put the data into that first argument, in tidyverse functions that works. In LM though, if we look at the help file for LM, we see that the first argument is the formula and the second argument is the data. So if you just pipe the data into the argument or into LM, it's going to put the data before the formula, and that's going to be a problem if you don't explicitly call it. But so whenever we use that period, that's the placeholder that tells R, hey, whatever's coming in from this pipe, put it where this period is. So in our function LM, we're going to tell it our data equals period, which means this data frame that's being piped in, and our formula is the outcome is IAT change, and it is regressed on the intercept only. So this is the same as if I took off this pipe and instead just ran it as model 1 and said, data equals bias, IAT change equals, or IAT change regressed on 1, or model 1, IAT change regressed on 1, bias. So this, because again, I'm just trying to make this clear, because the formula is the first argument and the data is the second argument, if you put them in that order, you don't need to say data equals. But I always prefer having my data be my first argument. Because it's the tidyverse way, but even in functions where it isn't supposed to be that way, as I read my functions, I like to start with knowing what data am I using for this particular thing, rather than looking at my variables first and then after that looking at what data set those variables come from. So I personally don't like this order, and I won't use this order. So I just use this data equals period, comma, and then put in the formula. So we're going to store this LM as a thing called model 1, and again, I actually do, I will keep it this way just in case the piping confuses somebody. I'll leave this on here because you can do it this way. But we're going to create a linear model object called model.1, which is from the bias data. We want to have IAT change regressed on the intercept. So now we have this model, and we need to look at some summary statistics for this model. So we'll look at this function called summary, and we just put in our model into the summary, and here's what it will output. Now you remember earlier we created fstat plus like our SSEs and degrees of freedom, etc. So if we look down here and we check out what our fstat was, you'll remember our f was 49.3637, and here this gives us a t value of negative 7.026. Well, you may notice that if you square this value, it will give you 49.37, because t squared equals f. Like this number and this number are directly computable from one another. If you take the square root of the fstat, you'll get your t value, or if you square your t, then you will get your fstat. For our degrees of freedom denominator, from where we manually computed it, we had, if you recall, we had 77, and here it tells us we have 77 degrees of freedom in that denominator. And then our p-value, if we look at that pval.xx variable that we created, it was, it's the exact same as this p-value that's reported here in our model summary output. So all this information that we computed by hand is available right here in this summary, where again, t squared is your fstat. It gives us that degrees of freedom for our denominator, and here is the p-value that we're looking for. So as far as the R side of stuff, that's all we have for this week. If you have any questions, let me know, and I will be more than happy to work things out with you.